Greetings! In this video, we will explain to you about bipolar junction transistor, also known as BJT. We will further explain about the type, basic structure, symbols, operation of BJT, the construction and characteristic of graph, and also to provide one calculation example for BJT. There are two types of bipolar junction transistor, which are NPN transistor and PNP transistor. You can see the basic symbol in the diagram below. In the NPN transistor, we can see that the current flows from the collector to the emitter when current is applied to the base, while for the PNP transistor, the current flows from the emitter to the collector when current is applied to the base. Here are some of the examples of transistors which apply NPN and PNP in their configuration. For an NPN transistor, as you can see from the circuit symbol illustrated, the voltage between the base and emitter is known as VBE. The base terminal is always positively charged in relation to the emitter. Meanwhile, the VCE represents the collector supply voltage in relation to the emitter. For an NPN transistor to enable conduction, the collector must be able to consistently hold a more positive charge in comparison to both the base and the emitter. In a beta model, the transistor also functions as a current-operated device. When it is switched into the fully on state, a large current, IC, will flow smoothly between the collector and emitter terminals. The DC current gain in an NPN transistor is beta, which is the ratio of collector current to base current IC over IB. The value of beta can be large up to 200 for standard transistors. On the other hand, for a PNP transistor, it closely resembles its NPN BJT. It only differs in the reversal of polarities for both current and voltage directions. As you can see from the circuit symbol illustrated, the VBE is negative at the base and positive at the emitter, and the base terminal is consistently biased negatively in relation to the emitter. The emitter must sustain a more positive charge than both the base and the collector for a PNP transistor to enable conduction.
Let me introduce you to the symbol for BJT. The following is the BJT symbol, and it is divided into two, namely PNP and NPN. Next, we find that there are three letters in the diagram, which are B, C, and E, where B represent the base, C represent the collector, and E represent the emitter. Now, let's move on to operation of BJT. So how BJT works? We find that BJT works by using modes of operation, which are divided into three. There is cut-off, active, and saturation. Here, we will tell you what the operation modes is. As we already know, it is divided into three, and the first one is cut-off. Cut-off occurs when the base emitter junction BE and base collector junction BC are in reverse bias, which means in this state, there is no significant current flow between the collector and emitter. The transistor acts as an open switch and doesn't conduct. The second is active, where BJT will work as usual and base emitter junction BE in forward bias and base collector junction BC in reverse bias. That means the small current that flows into the base control is the larger currents that flows between the collector and the emitter. This property allows the BJT to amplify the signal. And the last one is saturation. In this region, both the base emitter junction BE and base collector junction BC are forward biased. The transistor also is fully on, and big current goes from collector to emitter. It is also behave like a closed switch, allowing maximum currents flow through it. Next, let's go to how to use BJT. First, to make sure the BJT works properly, the PN junction needs to be properly biased with an external DC voltage. Now, let's take a look to the picture. As you can see, the picture has shown which one is forward bias and which one is reverse bias. Did you know what's the difference between PNP and NPN? So the difference between PNP and NPN is PNP transistor needs a positive charge between the base emitter junction BE and base collector junction BC to operate, while the NPN needs a negative charge between base emitter junction BE and base collector junction BC to operate. Actually, NPN and PNP has similar working principle, but the current direction and voltage polarity are different.
Okay, for this part, I gonna to talk about the graph. As you all can see, this image show a input graph, which is IE is the emitter current against VBE is the voltage across the base emitter junction. So this graph is used for various purposes in electronic circuit analysis and design, such as piercing point determination, transistor amplifier design, and identification of operating regions. So, in summary, this graph is a valuable tool for transistor analysis and design, providing essential information for BAC, amplifier optimization, and understanding the transistor behave under varying input conditions. So, this is the next slide, which is show about the output graph. So, this output graph it show the collector current, which is IC, against the collector emitter voltage VCE for various value of base current. As you guys can see, there is a red line on the graph. This red line is called DC load line. So what is DC load line is for? According to the Google, the DC load line is used to determine the correct DC operating point, often called the Q point. So, in summary, this output graph is used to design amplifiers, set the operating point, and ensure the transistor operators in the linear and saturation regions as required for signal amplification. So this is for my slide. Thank you.
This is an example question for fixed bias configuration. From the diagram, we need to calculate IB, IC, VCE, VB, VC, and VBC. The value for beta is 100. By using Kirchhoff voltage law, we're going to get VCC minus VRB minus VB is equal to 0 on the base part. And use Ohm's law and rearrange the equation, we're going to get IB multiply RB equal to VCC minus VB. The final equation we're going to get is IB equal to VCC minus VBE divided by RB. To find IC, we need to multiply beta with IB. Then, on the collector and emitter part, we using Kirchhoff voltage law and we going to get equation VCC minus VRC minus VCE equal to 0. Then use Ohm's law and rearrange the equation, we're going to get VC equal to VCC minus ICRC. To find VBC, we're going to use equation VBC equal to VB minus VC. After that, follow the equation that we got just now and insert the value into the equation. For IB, we're going to get 47.08 microampere and IC is equal to 2.35 milliampere, VCE equal to 6.83 volt, VB and VC we are going to get 0.7 and 6.83 volt. And last, we're going to get VBC equal to negative 6.13 volt.
That is all from us. Thank you. We hope you enjoy our video and are able to further understand about the bipolar junction transistor BJT.